the situation in a database is only getting worse or more complex than the simple museum example I gave you. Right? Give you an example. Multiple users may update, may access and update your database. For example, suppose you build a database for the University of Utah admission database, right? So we update college, set enrollment equal to enrollment plus 1,000, where college name equal to U of U, meaning some administrator from Utah has been informed that we have admitted 1,000 more students, and you need to update that value in the database. That make sense? We call this administrator admission officer 1. Admission officer 1 is doing this while the other admission officer is informed that we admitted yet another 1,500 students. Meaning by the end of the day, the total number of enrolled students should have been increased by how much? 2,500. But if you do not have concurrent control in the database, what would you end up with? You may end up with any one of the following. Suppose the current value of the enrollment, of course, is X. You may end up with, which is the correct answer, X plus 2,500. If database executes the first statement completely before executing the second statement, or the other way around, then you got the correct answer. But you may also end up with possibility number 2, which is plus what? 1,000, right? Why? I read the value of X. The second person read the value of X. Second person increase X by 1,500, write it back. First person increase X by 1,000, write it back. So the final value is equal to X plus 1,000. Using a similar argument, but the other way around, you may also end up with X plus 1,500. So that's the problem. Does that make sense? So this is what we call attribute level inconsistency, meaning you have an inconsistent value with respect to a particular attribute value, in this case, in number of enrolled students. So this we call attribute level inconsistency. You may also have a tuple level inconsistency or record level inconsistency. Here is an example. Same admission officer 1, same admission officer 2, trying to update the database at the same time. For student ID 123, so this is the student ID, so obviously there is a student record corresponding to this particular student. And that student record may look like, let me give you an example. So this student record may look like from the student table, somewhere in this student table, there is a student record that has student ID. So the other I don't care. These are other values, right? Which is equal to 1, 2, 3. And this attribute has multiple values, like name, I don't know, Feifei, and some other attribute like age, I don't even care, so on and so forth. But there is an attribute called major. Let's say my major initially is undecided. It's 2BD. Does that make sense? And my decision, admission decision, initially is TBD as well. So Feifei has applied to University of Utah. They haven't decided whether to admit Feifei or not. Okay? I mean, the answer obviously yes. Come on. But let's run through the points. So 99% of chance they will say yes. Okay. So admission officer 1 read this record, while admission officer 2 read the same record. And both of them get this value, which is 1, 2, 3, TBD, TBD. Right? And one changed this to major to CS, the other changed this to yes. You follow me? Now, no matter what happens, you're not going to get the correct answer in the end of the day. Either you have major equal to yes, admission decision is still undetermined, or you got admission decision is yes, major is undetermined. When you have this scenario. So what's the only possible scenario to get this right? Well, let one person do his job or her job before letting the second person come in and do his or her job.
So, okay, I'm still confused because you saw the SID isn't changing, so I'm not seeing why, like, how the inconsistency happens.
Well, the right consistent value at the end of the day should be what? Be this, right?
Yeah.
But when this person reads this first, and before this person writes the updated value back, the second person come in and read the record of this whole record, not only just the attribute.
The whole thing.
Yes.
Okay.
Suppose database return the whole record. I mean, if you think about the way database works, when you do update, right? Conceptual evaluation says you find the record, update the attribute, and go back, and write back the record. So it operates at, assuming database will operate at the record level, then this may happen. Okay, cool. And you may also have table level inconsistency. This is even worse, right? Let me finish this and I'll take you worse. And this happens all the time actually in practice. Very, very common, okay? I'm gonna update the apply table and update the decision to yes from undecided. For all the student records where GPA is greater than 3.9, their high school GPA is greater than 3.9. Does that make sense? And this may affect hundreds or thousands of students, depending on how many have applied to university and how many of them have a GPA greater than or equal greater than 3.9. Yes or no? Yes. Okay. So this, and obviously this process may take a while, depending on how large the table and how many records are being affected. This may take from a few seconds to a few minutes, even a few hours, if your table is super big, like billions of records. Obviously, unlikely for applied database, right? But you can make a similar argument to some other large database with billions of records. Does that make sense? Now, the other admission officer decide to do the following, which is, I'm gonna give a curved GPA for students from a really large high school in his or her high school study, which makes sense. A 3.9 from a high school with only 2 students versus a 3.9 from a high school with 2,000 students. You want to weight that 3.9, the second 3.9 a little bit more in your decision making than the first one. Final 4 is called Final 4 because you have hundreds of teams to begin with. Final 4 means nothing if you have 4 to begin with. Of course, you can still call Final 4. Yes or no? But if you only have 14, you call Final 4. You don't call March Madness. Right? You call whatever, March show game, showtime, whatever. Right? But not March Madness, for sure. So that's what's going on here. So what happens? Can someone explain to me what happens now?
Are they going to both go through the same time?
Yeah.
Updating rows and some couples from one period or one updated one? Yeah,
when both are happening at the same time, you may make wrong decisions. a student with less than 3.9 GPA from a high school of 2,500, more than 2,500 students, if his or her GPA is above 3.9, divided by this, he or she should be admitted. But when you execute both of them in the same time, this person may lose out this opportunity. First condition is when size okay. And this becomes even worse. Oh, right. Forgot to take your question. Go ahead.
So going back actually to the section before this last one. Going on
the last one, this one? Okay.
Yeah, this one here. Going along with Dylan's question, I think. So when you're executing an update,
yes,
is it like under the hood? I guess is it updating every single field, or is it just updating the field that you say? Like we're saying set major to this. Is it just updating that, or is it updating every single thing what we have?
So what you're asking is how database actually update a record. Does the database update only the affected record, or take the whole record out and write it back?
Yeah.
Is that your question? That depends on, this is something called granularity of your log. I don't want to go into this, but since you asked, granularity of your log. So database manage this inconsistency issues through the means of log, kind of like a semaphore. And it really depends on what's the granularity level of your log. Some databases choose to log the whole table. Obviously, that's very safe, but efficiency suffers. When you log the table, nobody can do anything to that table. When you log the record, nobody can do anything to that record. When you log the attribute, nobody can do anything for that attribute, but then they can do other things for the other attributes. So it really depends on the level of your granularity. If you think about in this case, if your level of granularity of your log is at attribute level, then you cannot prevent this from happening. You have to use a granularity of record level log to prevent this from happening. But the next slide shows you granularity of log at record level may not be good enough. That makes sense? Even if you log every single record you are trying to update, you still run into inconsistency issues like this. That make sense? So this shows you solving this problem actually is tricky. It's not that tricky. Really.
So would you have to have, I guess, then to make it like safe, is have like hierarchical locks, I guess, where like if you lock the record, then nobody can acquire the lock for the whole table, which would be like
yep.
above one need.
So a typical approach in database engineering is to use a hierarchical adaptive locking approach. Does that make sense? To try to figure out the best way to ensure such inconsistency doesn't happen. And in the undergrad level database class, I'm not going to go into detail of that. We just simply don't have the time for it. But you can have some high-level understanding of, based on this discussion. If you're interested in all the details, again, take the database system in the grad level, where we'll talk about locking and all that stuff. Okay? Multi-statement inconsistency. So far, if you think about it, the example I gave you can be addressed by using a super log, meaning I simply log my table, or even worse, I log my entire database. Meaning when I'm doing some update, nobody mess up with my update. You have to wait. Of course, efficiency sucks. Imagine if Amazon.com database takes this approach, what happens? What happens? Well, you will have, in 2 weeks' time or 2 months' time, you will have another website called AmazonB.com. I guarantee you that. i.e., Amazon.com will go out of business. Period. No? Nobody's going to use a website like that. I want to order something, you ask me to wait like 10 minutes? Are you kidding me? I want to spend money. And you tell me to wait. It's not like I take money from you, right? I'm giving you money. Right? So you go out of business. Period. like no time. Okay, so you cannot do this. But even if you don't care about that, even you don't care about efficiency issue like this, you say, fine, I lock the whole table, you wait. I don't care, you just wait. Even you do that, that sometimes doesn't really solve the problem. Why? Because you may have multi-statement inconsistency that affects more than one table. In other words, the only safe solution is really to lock your entire database. And that approach, obviously, in practice, cannot scale. Give you an example. I'm going to take the admission decision no, meaning those students who are rejected. Take them from the active applied table and put those records into the archive table. Why I no longer consider these records in this application season, but for analytical purpose, I'm going to keep these records in some safe place. So for future analysis, like how many applied, how many admitted, where they are from, and diversity, and so on and so forth, I want to keep a record of that. So I take the no decision to insert them into archive database, and I then delete from the active applied table where decision is no, obviously. You take them away, then you delete them. You insert them into archive, then you delete. Does that make sense? You have to do it this order. You cannot do delete first and then insert, right? Because by the time you do insert, the records are gone. Right? Well, another person may be doing some analytics at the same time. Like US News always rank universities, right? And one critical factor they use in the ranking, do you know is what? How selective the school is. How many apply, how many reject. Yeah? And US News person might do this query. Now you have wrong, right? Does that make sense? Because you count and your calculation will be off if you don't control this carefully. Okay? So that shows you a problem. So the goal of concurrency execution in a database is to ensure a sequence of not only a single SQL statement from this example, ensure that a sequence of SQL statements can be executed concurrently. That's the objective. If you run them one after another, meaning one job after another job, that's a safe approach, safe and sound. But your database efficiency and scalability suffers. Nobody's going to use a database like that. Does that make sense? So the goal is to ensure the execution of multiple statements concurrently, safe and sound, so that they appear to be running in isolation. What does it mean in running in isolation? The keyword is isolation. Think about this as two persons, person 1 and person 2. The design objective is so that person 1 and person 2 at any given time can issue these statements without worrying about who else is running some job in the database. In other words, like I'm running the database in isolation by myself, even though I know for a fact that there could be other users actively using the database. But the underlying database is designed in a manner that I, as a user of database, do not have to worry about these issues. So this is what we mean by run these statements in isolation. So simple solution is to execute them in isolation, which means job 1, job 2, job 3. Putting into perspective, if you go to Amazon.com, I record the timestamp the first time you arrive in Amazon.com, and then rank users based on that. First user has to finish all he or she wants to do before the second user can proceed. Kind of like going to a restaurant, they give you kind of this beeper. You go, and 60 minutes, 40 minutes later, they ping you, you come back. But for Amazon.com, with millions of users, I don't think you're talking about 30, 40 minutes. You probably talk 30, 40 hours. Ping you, oh, it's now your turn, come back and do it. Right, so this is one simple solution, meaning really execute them in isolation. Doesn't work, okay? So this brings up the concept of transaction, which I show you already. I'm gonna skip this particular slide because that's exactly the same thing I demonstrated to you last lecture. How to issue a transaction in a database system. Okay? Start transaction, either then commit or rollback. By default, most database systems using auto commit equal to true, meaning every single statement is viewed and treated as a transaction, so that you don't have to explicitly write start and commit statements yourself. But if you have multiple statements and you want to make sure all these statements are treated as a single transaction, you have to explicitly write start transaction and commit to enclose these statements. Otherwise, each one of them will be treated as a separate transaction by itself. You may wonder what's the difference. The difference is transaction, like I said last time, is atom. It's like all or nothing. If you want to make sure at the end of the day, the set of statements is like all or nothing. Like this. Meaning when system failures, when you have a system failure, I want to make sure none of the insert or delete has happened. If you treat each statement as a transaction, you don't get that. Because system might fail after completing the first insert statement in the middle of executing the second delete statement. If you use auto commit equal to true approach, system failure means that it will only roll back the delete statement, not the insert statement. That make sense? You want to make sure both, like nothing has happened when you have a system failure. You have to include both in one single transaction. So you cannot use auto commit equal to true approach in that scenario. Yes?
So do you get like all of those, like you turn auto commit off and you don't explicitly do a transaction, do you get like all of those inconsistencies, like attribute level stuff and all of that? Or does it only matter for when you're doing multiple statements?
Yeah, when you disable auto commit equal to false, the behavior of the database depends on the particular database server you use. It really depends on what they implement. So the answer is I don't really know. You have to check the particular database server, what's the behavior in that situation. One possible scenario is they view everything as a transaction until you issue a commit statement. Then those consistency issues will still be taken care of. But if you don't commit and system fails, you lose everything. That makes sense? So it really depends on the behavior of your database servers. Okay. So the answer is really depends. In particular, in MySQL, if you guys in the future want to use transaction in your development and you use MySQL as a database server, MySQL has two different storage engines. One is called MySAM, the other is called InnoDB. Only InnoDB supports transaction processing, so you want to make sure you use the InnoDB storage engine. Okay. You may wonder why don't they support transaction by default? Because supporting transaction is expensive. It introduces non-trivial overhead to your underlying database server. If you have a database that's warm database, so what's a warm database? Not a database of worms. Okay. Warm database means write only, read many. And I wish we can have a database of worms. That's probably wrong. But we don't. Warm database means write once, read many, meaning it's an analytical database. Then you don't need transaction. Transaction actually slow you down. You go with storage engine like MySAM, where they drop the support for transaction. And for that, database become quote unquote more lightweight, meaning more efficient. But if you have an update-intensive database, like a banking scenario, banking database, people deposit money, people take money out, what happens? You want to have transaction support. Otherwise, you run into problems, right? So that's only one reason people use transaction. The other reason people want to use transaction to guard against is resilience to system failures. For example, I do a bulk insertion or bulk loading to the database. Like this is an example of bulk insert or bulk loading. I take a bulk of records from one table and insert into another and delete the bulk record from the first table. I want to make sure this whole process is kind of like an atom or semaphore. All of them must complete, or none of it doesn't complete. In this particular case, you may wonder, it doesn't really matter. I'll give you another example where I want to give interest, 10% interest to all my bank accounts, bank users. You want to make sure you treat everyone fairly, right? Everyone either receive that 10% interest or none of them receive that 10% interest. No matter what happens in the process of doing this. You cannot have this random set of users get 10% interest, but the other may not in case of system failures. I don't even know who get it, who don't get it. A bank cannot use a database like that. Does that make sense? So resilience to system failure requires database system to support transactions, meaning there is this abstraction from your underlying database system such that if I use transaction and if I commit, if I have committed before system failure, I don't care what you do. Do whatever that costs you. Do whatever it costs. You have to recover the changes I made to your database. But on the other hand, if I haven't committed, this abstraction tells me, as a user, I can rest assured, no matter how many changes you have made so far, maybe none of the changes you have made, or you have made 99% of the change, or you have made 50% of the change. As long as I have not committed yet, and system fails, I can be assured, I can rest assured that it's like nothing has happened. That makes sense? This defines resilience to system failure. Yes or no? Now, connects back to your U-track system. When I say, oh, you want to make sure user documents the visits he or she has to multiple POIs through something like a session and only commit in the end. That's something, when you do that commit in the end, in practice, in the real world, to do it right, you want to enclose all those updates in a transaction. Otherwise, if system fails, what happens? If user has documented 10 visits to 10 different POIs, you may end up recording 5 of them in the database, or 6 of them, or 3 of them, but lose the other ones if you don't use the transaction. That said, do not take this as the wrong message that I'm asking you to use transaction in your implementation. I'm not going to restart server in the middle of your test of your phase 3. Okay? And we have about 100 users at most, and they all accessing different databases. Only maybe 1 or 2 users are concurrently accessing your database at the same time. You don't have to worry about these issues. But if you try to take your U-track system and commercialize that, well, you better worry about these issues. Does that make sense?
So you say use cases requiring transactions are more common than the like worm?
Worm? Oh, in practice, I think it's half and half. What I mean by that is, for mission critical database, you always want to use transactions. Like military database, you talk to FBI. No, disclaimer, I never access any FBI database. Okay? Don't take me like, oh, you know. But it makes sense, they will use transactions. Bank, yes. But in practice, if you go to, I'll give you an example, like Expedia.com. While you're pulling records from database, showing what hotels are available and all that, probably they don't use a transaction for that, because that's a heavy weight for that. But when you are making your booking and finalize your booking, commit that to the database, I'm sure they're using transactions. So even for the same database application, they may choose to use transaction or not to use transaction, depending on what you're doing with their database. Does that make sense? Because reading what hotels are available at what price, sometimes you actually get that, right? You read this hotel, when you try to book, they will tell you this price is no longer available. That's probably because they didn't use transaction to guard against that, so that somebody else changed the price or make a booking, and that rate is no longer available. If you had used transaction, that second person should not be able to make any change while you're viewing this record. But obviously, that's not mission critical. User is not going to be annoyed by that. They just do updated search. But if you finalize the booking, try to commit, and after you commit, you finalize the booking, it will be really annoying to the user. Expedia comes back and says, oh, your booking is no longer valid. That make sense? So I hope that explains you. Yes?
So let's say two people, they both made whatever changes. One is doing add and delete, one wants to count to the same thing. If they both click on commit at the same time for the transactions, will that cause inconsistency, or will that still work?
Why don't I answer that question, because I have slides detail for that. So I skip this, I talk about this. So guarantee all or nothing execution regardless of failures. The solution for both concurrency and failures is transaction. And transaction in high level is a sequence of one or more SQL operators or SQL statements treated as a unit, quote unquote, atomic unit, like an atom. And transactions appear to run in isolation, and if the system fails, each transaction's changes are reflected either entirely if transaction has committed, or not at all. If transaction has either go back on itself or hasn't committed yet at the time of system failure. Okay? In a lot of database systems, they don't require you actually, if you auto-commit is equal to false. This goes back to my response to Dylan's question earlier. If the auto-commit is false, in a lot of database servers, they actually don't require you to start that statement called start transaction. By default, automatically, they treat your first statement as the start of your transaction until you see a commit or rollback. Does that make sense? But my recommendation is for you guys to make your code readable and comprehensible by a third person. Always start with start transaction, even if database server does this automatically for you. That's a good practice to keep in mind. So that when people trace back your code, they know, oh, this is the start of your transaction, this is the end of your transaction. Okay. Now I'll answer your question. Now we have to define when transactions ensure isolation, what do we mean by isolation? Because one simple definition of isolation is what? Is to run them in isolation. But even in that case, I don't know whether you guys realize or not, her question implies this answer somewhat, which is, fine, let's say I'm gonna do isolation using this approach of true isolation, meaning one does his job first, then the second person does his job, or her job, without any concurrent execution of any statements from the two jobs. You still have to make the decision. Database has to make the decision which one to execute first. Does it make sense? Yes or no? You may argue, okay, in the Amazon.com example, fine, let's look at who arrived at Amazon.com homepage first. Look at the timestamp. Point taken. That's probably one possible solution. But what if, remember, clock, human clock, can only be, has a precision up to a certain point, milliseconds or microsecond. The universe is continuous. Time in the universe is continuous. But human measurement is always discrete. What that means? What does it mean? What does it mean?
So, I mean, because time in reality is continuous, like probability that you have two things happen at once,
yeah.
0, but because it's really measured discretely,
exactly.
It's possible to have
yeah.
them be the same.
If you have that almighty person, that person can tell the difference, who is first. Human system cannot, unfortunately, in certain cases, because you have a precision of your clock. So going back to the Amazon.com example, you argue, okay, I'm gonna order them based on the time of arrival. But what happens if you have hundreds of users? When you have millions of users coming to your website all the time, it's very likely hundreds of users, based on your clock, will show up at the same time. And which one's job you want to execute first? What do you mean by isolation in that case? Do I do user 1, 2, 3? Or user 2, 3, 100, 1? Or whatever. That's the discussion we're going to have next. I will continue on Wednesday.